Hi guys, we are Group A8 in Bionic, and my name is Yu Jing.
My name is Tianrui Wang.
My name is Tiancheng Yu.
So this is our 3D printed enclosure for our whole hardware system, and we're gonna use this hardware for our next demo.
So our chip is called a Neural Processing Unit, which is long for NPU, and it is designed as a hardware accelerator for calculations like matrix multiplications. And our technology node is the TSMC 65 nanometers, and we applied a comprehensive digital methodology to design our chip.
So for specific applications, since the chip is designed for AI computing, we're using the chip to complete an image recognition task. And for a vanilla version, we use the chip for the single handwritten digital recognition, which is actually called as the MNIST classifications. So now that's all the information for our backgrounds. We are ready to move to the demo section. Welcome to our first demo. So in our first demo, we have the entire hardware system in this blue box. This is the 3D printed enclosure for our entire hardware system in demo 1. And you can see that if we open the lid, you can see the PCB inside. So this is the PCB for the NPU, and this PCB is sitting on top of a Raspberry Pi, and all of their IOs are connected for a interaction. So in this hardware, we're using the Raspberry Pi as the host controller to interact with the NPU and then complete the entire recognition task. So on top of that, we have a PC camera connected to the Raspberry Pi, and we will display all the recognition results and process the image on the PC display that we have. So that's all for the hardware explanation. Let's move to the demo itself. So let's say I want to do an image recognition result. I have a whiteboard in front of the entire hardware system, and the PC camera can take an image of that whiteboard. So now let's say I want to recognize that I want to write a 4 here. So now we can do the recognition by clicking the space. So you can see that now you can see that now on the left side, this is the raw image that we captured. On the top right corner, this is the captured image from the orange square. And on the bottom, this is the pre-processed image from the captured image. And this is the image that we actually pushed into the NPU. And then after all the processing, we got the result that the result is 4, and it's back annotated on the raw image. You can see that you've written the number 4, and it's correct. So let's do the exactly same thing again, and now let's say I want to do the recognition for number 8. I read an 8 on the whiteboard, and we do the recognition again. So now you can see that on the exactly the same setup on my monitor, my raw image, my captured image, and my pre-processed image. Now the results is showing that you've written the number of 8, and this agrees with our expectation. So this is for our demo 1. Let's move to demo 2. Thank you very much.
Hello everyone, welcome to our second demo. So let me explain the setup here. This is a FPGA board, serve as the host of the NPU. This is the PCB board of the NPU, and we probe some of the signals out of the PCB board using the logic analyzer. The probe signals are going to be displayed on this monitor. And the monitor over here is going to show us the image that is currently being processed. So we can see that the FPGA board is currently not running, and there's no recognition result. But if I flip this switch, we got a recognition result, which is a 7, which is the same as the one on the monitor. And we can probe some signals out of the logic analyzer. The first signal here is the clock. This is one of the input, one of the output, and this is a control signal. We can pay special attention to this signal right here, which is called the read enable. This signal is pulled high every time we try to read a neuron from the NPU. So we can notice this very interesting pattern here, which is coherent with the way we designed our NPU. So these rising edges belong to the first layer, and these belong to the second and the third. The reason why the rising edges of the first layer take much longer because the first layer takes 256 input to compute one neuron, but the second and the third, they only take 16. Now we can move on to the second image, which is a 2, and we can see the recognition result. It's also a 2. The third image is a 1. It is also a 1. 0. And we also have a 0. So this demo is designed to showcase that our NPU can run under a much higher frequency than the Raspberry Pi demo. So that's about it for our second demo. Thank you.
Hello everyone, welcome to our presentation. My name is Tianchen. The other two members are Terry and Yufei, and our group is called A18 Bionic. Alfred is the TA for our project, and this course is instructed by Professor Kinget. Our project is called NPU MNIST Classifier. Let's start everything from a very high-level system overview. So the target of our project is to design a neural processing unit, i.e. an NPU, to accelerate the AI computing process. And because matrix multiplication is a very important type of execution in AI computing, so essentially what we're doing here is that we want to design a hardware accelerator to accelerate the matrix multiplication process. And because we're designing hardware for AI computing, we're choosing a vanilla scenario for our application example, in which we ask our NPU to complete a single handwritten digit recognition task, i.e. the MNIST classification. So the entire system can be represented by the block diagram here. So we have an image with a single handwritten digit, and we push this image into our chip or our system, and we're expecting that the system can generate information that the number is 3. And for MNIST database, it's just the public data set with tens of thousands of images of single handwritten digits, and it covers a wide variety of different handwriting styles, so it's a very good resource for our training purpose. And to realize our task, we propose our neural network structure like the figure on the right. So totally we have 4 layers, and for the input layer we have 256 neurons, and for the output layer we have 10 neurons. And for the two of the hidden layers in the middle, we have 16 neurons for each. And the total number of MAC operations required to complete the inference process of this neural network is around 4,500. And then regarding the training and inference process for our neural network, the training is done in TensorFlow based on the MNIST dataset, and it will obtain all our parameters, including the weights and biases in the TensorFlow framework. We want to emphasize that in our project, our chip only focuses on inference, so we'll assume that we already obtained the parameters, including the weights and biases from the TensorFlow, and these weights and biases are ready as inputs for the chip to complete the inference process. So this is the methodology that we used for our NPU design. So we started everything from a high-level NPU concept, then we used the TensorFlow to construct our neural network model, then we digitized everything and construct a fixed point model in the MATLAB, then we construct our block diagram data path structure to represent the behavior of the model in MATLAB, then we used the RTL modeling to model all the behavior of the data path structure. Then we iterate the entire process from the MATLAB all the way down to RTL coding from V1 to V7.1. And after that, until we are satisfied with our RTL modeling, we designed a comprehensive test bench to verify all the possible modes of our NPU. And after that, we synthesized our netlist using a synthesizer and use exactly the same test bench to verify the entire netlist. And after that, we used the digital float tool to get our PNR core. And we also propose some custom circuits like input and output buffers and Schmidt trigger. And we combine these custom circuits with the PNR generated digital core to a integrated core. And after that, we combine this integrated core with the peripheral circuits like ESD and DCAP. And finally, we have the JDS. Then after that, we send the JDS for a AMS verification on the transistor level. And if the JDS could pass the AMS verification, we said that the entire thing is finally ready for tape out. So this is the architecture that we used for our NPU, and this is the final version, which is V7.1 that we actually use for tape out. So on the left side, this is the top level on-chip block diagram, and you can see that there is an NPU core in the middle for the computation part, And we have a finite state machine provide all the controlling signals, and we have a register to store all the configuration options. And if you expand the architecture of the NPU core in the middle, you get the block diagrams on the right side. And in this, you can see multiple blocks are working collaboratively to complete the entire computation process. And we want to emphasize that the core computation is realized by the MAC module here, i.e. the multiply and accumulate. In this module, it can take two inputs and then multiply them together and add and send the result to the adder and accumulate with previous added results. So we can use this module to achieve the entire matrix multiplication process. And after that, the result goes to ReLU, which is the hardware realization of the activation function that we choose for our neural network structure. And this module will basically find the maximum value between your input results and 0. Then after ReLU, the result goes to a pixel, which stands for parallel input and serial output. So we use this module to compress the results from ReLU to a smaller number of bits so that we can reduce the number of output ports. And the output of a pixel will go to FIFO, which is standard block for first in and first out. So we use this block as a temporary buffer to store the result from the pixel, and the user can basically put one read-enable signal high to choose whenever to read the signal from the NPU or not. And the count module stands for comparator, and they are connected to the ReLU output. And basically this module can compare the results from two ReLU and decide which one is larger. And it will compare the larger one to the largest value so far that has been stored inside, and it can replace the inner value with the largest value so far. So basically we use this module to get the largest value so far, and basically it can be used to accelerate the inference process for the final layer. Since we don't need to actually know the neuron value in that layer, we only need to know the index of that particular neuron with the highest value. And finally, the debug stands for debugging engine. It has many probes inside the system, and it can take samples of different things and shift this data one by one to the output, so that we have access to these internal signals after the chip has been taped out, and we can use this debugging engine to make sure that we know what is going on inside the chip for the post-silicon stage.
So let's go over the process of NPU verification. Before place and route, the verification was performed in Model Sim using Verilog test bench. And after place and route, we verified the NPU digital core together with the buffers and the Schmidt trigger in Virtuoso's analog/mixed signal simulation, or the AMS. All the verification processes were based on the 5 tests that we designed to verify the functionalities of NPU. They're listed on this slide. So let's take a look. The first test is we tried to verify the manual control and the ReLU bypass function. In the second test, we verified the comparator function, both the largest and the index output. In the third test, we verified the debugging system, i.e. the debugging pixel. In the fourth test, we verified the entire inference process with FSM control and the outputting pixel. In the fifth test, we verified the entire inference process with FSM control, the FIFO, and the comparator. We'll go into much more detail on our website. The tab is called verification.
So next, moving on to the pinout of our chip. Our design features 2 distinct voltage domains, one dedicated to the I/O and another to the NPU core. For the core VDD, there are 4 pins which are connected to the VDD of the NPU core. These are placed in the upper right-hand corner of the chip to ensure a clean power supply to the core circuits. On the other hand, the I/O VDD has 2 pins which are connected to the VDD of all I/O buffers and Smith triggers, along with the ESDs for this domain. As you can see in the figure, there are 2 groups of I/O VDD pins. One group is located at the upper left corner of the chip and another at the lower right corner. This arrangement allows a balanced power distribution to all I/O components, and the remaining pins serve as the chip's input and output signals. The output signals are grouped in the lower left corners of the chip, and the rest of the pins are assigned as the input signals. In the figure to the left, we present the floor plan of our layout. To the right is our finalized chip layout. As previously demonstrated in our pinout section, The top left and the bottom right corners are allocated for I/O VDD, and the top right corners are dedicated to the core VDD. The input buffers, output buffers, and Smith triggers are placed adjacent to their corresponding pins for optimal signal integrity and better performance. The NPU chip is positioned at the center of the chip, and every input and output pins of the core are connected through signal lines to the corresponding pins on the pad frame. To maximize the use of space, decoupling capacitors are situated at the four corners of the chip. The entire chip is architected with a high degree of symmetry to cancel out electromagnetic fields generated by the currents in the circuits, reducing electromagnetic interference to enhance the chip's performance and reliability.
So let's take a look at the PCB and the enclosure. On the left side, you can see the NPU PCB, and at the center of it is the NPU chip. Because we like to keep the design compact, we chose to not use the socket. Surrounding the NPU are the level shifters, which are used to down-convert input signals to the NPU from 3.3 volt to 1 volt, and to up-convert NPU output signals from 1 volt to 3.3 volt. On the right, we have the headers for Raspberry Pi I/O board, which is for demo 1. On the left, we have the headers for the FPGA board, which is for demo 2. We can see the enclosure of the PCB on the right side of the slide. The NPU PCB is sitting on top of the Raspberry Pi I/O board, and they both fit right into the enclosure. We also designed a mounting hole for the webcam. The enclosure also has a slot for the power bank and an opening for the USB hub to come out. This is the setup for demo 1, and it's the same as what we've seen earlier in this video. On a very high level, we have our webcam pointing at the handwritten number, and the captured image is going to be pre-processed and downsampled to 16 pixels by 16 pixels. Then we feed the image together with the weights and bias of the neural network to the NPU and let it do all the computations. The laptop on the right is SSH tunnel to the Raspberry Pi and displays the raw image and the pre-processed images. After the recognition result is back, it's going to be back annotated on the raw image. We should note that the Raspberry Pi is struggling to drive all the IOs, so we could only clock the NPU at 2 kilohertz. So this is the demo 2 setup, and we've also seen this. On the left, we can see the NPU PCB, which is sitting on top of the FPGA board, and we have a logic analyzer that probes 4 signals out of the NPU PCB. On the right, we can see the monitor that displays the current image under processing. The recognition result is indicated by the 7-segment display on the FPGA board. We designed the second demo to showcase that NPU can run at a much higher frequency compared to the 2 kilohertz that we've seen in demo 1. Now the highest we can clock NPU is at 6.25 megahertz. We will go into more details on both demo 1 and demo 2 in the website.
So now finally we're ready for a conclusion. Besides the results mentioned by Tianrui, we actually used the NPU to classify 100 different images. And because we will obtain 42 neurons for each image, so totally we have 4,200 different neurons. And we compare all of the neurons to the golden model we established in MATLAB, and we've validated that every single neuron generated from our NPU matched with the results from our golden model, which means statistically our computing mechanism is trustworthy. And on the right side, we actually compared the results from the NPU to the software solution, and we have some interesting results here. So you can see from this table that if you run the entire inference model using only the Raspberry Pi on the software solution, i.e. you're doing everything just in a standard CPU, and you run everything at the 1.2 gigahertz frequency, the computation period for one image will be 0.14 millisecond. Whereas for the NPU case, if you use the FPGA plus NPU solution, and if you run it as the higher frequency that we're supporting here, which is 6.25 megahertz, the computation period would be 0.36 milliseconds.
because this is already the highest frequency that we support. So you can see that this is even slower than the Raspberry Pi itself. So it appears that we just designed a hardware decelerator. But if you look closely, you can see that for the software CPU solution, you are running everything at a 192x higher frequency, but it results only 2.5x faster, which means you are using much more power to do the exactly same thing that an NPU would do, which will prove that NPU is doing something in a much more efficient way. It's just because two systems are running at different frequencies so that the throughputs are different. We do have some current issue now. We observe that chip will stop working at a frequency higher than 6.25 MHz, but our nominal design point is 10 MHz. We suspect this comes from a very large VDD ring on the PCB, and this very large VDD ring could cause bit flips inside our chip. We will try to add some more DA cap to our chip, or add an additional VDD plane to minimize the inductance. We are still trying to resolve this issue, and hopefully we can solve this issue in the future. It's time for acknowledgement. This is the brand new project from the course, and the logistics behind this project is fairly complex. To achieve this project, we reach out to many people for help, and we want to express our sincere gratitude to all the people who help us during the journey. The project won't be possible without many people listed here. And finally, we are so proud and glad that we achieved everything, including the chip testing and chip design in just 2 semesters. Finally, we made it. Thank you very much.